More time? More time? Yeah. Good? Yeah, everybody's good? More time? All right, okay. Back to the actual lesson. Okay, recall the following types of transformations. Here's a list of them. Now, if in your brain you're like, I still don't know vertical, horizontal, I don't know what you mean by stretch, compression, I don't know what you mean by translate, that's okay. That's all going to come on the lesson. That's just a guide of where to find those things. And that guide actually comes right from quadratics. Quadratics in grade 10, you did all those things. You used maybe slightly different words, but you were just finding where did the vertex move to, did it flip over, you know, that's been going back since grade 10. So, in particular, our study of transformations will be applied mainly to the following functions. Linear, that was grade 9, y equals mx plus b. Quadratics, square roots, 1 over x. b to the x, which could be 2 to the x, 3 to the x, 4 to the x. Sine x, cos x. I'll just put question marks beside those. Those could come up in the homework, and I'll do an example today. We do want to review that a little bit, but in the end, I move all that stuff to chapter 6, where the actual trig chapter happens, okay? So we'll look at them, but not too crazy, and definitely absolute value. Like the opening question of the test, I usually do 2 or 3 questions where you have to do these transformations on one of these functions. I just randomly choose a couple of these, but you just got to count on absolute value being there on that first page. It's the new one to the party. It's part of advanced functions. You got to know I'm gonna choose that as one of the functions. So the purpose of the following table is to refresh your memory about some of the transformations. Okay, I'm going to do 2 things with this table. One, I'm going to act like, the first time I go through an example, I'm going to act like, yeah, I know the transformations. I know how that all works. Then I'm going to stop and go back and go, no, yeah, too much. Slow it down and show me exactly step by step. And I'm going to keep doing that in the examples till everybody goes, okay, I got the plan now. All right, that's the plan. All right. When you see a function, you're given a function, say on the first page of the test, maybe I choose this, y equals 3x squared plus 5. The first thing that's got to happen is, what is the base function? And your only choices that you'll get are these 8. Those are the big 8 at this point in your function career. So you look at it and go, which one is it? Hopefully it's obvious. It should be. You should be able to just look at it and go, oh, y equals 3x squared plus 5. That base function must be y equals x squared. Is that big enough you can read that when I do that? Is it okay? Yeah. Then you got to decide what are the transformations on this thing. And that's where my little chart helps. You go, there's a 3 out front multiplying this whole function. And you go back to this, and you got to get a memorized by the time you get there. What does a multiplier out front? Not the negative out front. We'll talk about a negative when we get to it. When there's a number out front, that's a vertical stretch or a compression. Here, because the number's a 3, if you're multiplying things by 3, that's stretching them. That's making them bigger. So that's a vertical stretch factor 3. Then, plus 5 outside the function. You go back to your chart, and you go, okay, when I'm plus 5, that means vertical translation up 5. Maybe, just maybe, you've gone from what a mess this chart is to like, oh, it's everything. It's the whole thing, yeah? It's a total guide on how to do these things. So here's the 2 transformations you get out of that. Boy, that looks small to me. Am I just old? I got to back up and see if that's big enough for you to read. I believe you. Some people nodded, but I don't know if I... Oh, yeah, I guess that's not too bad. You let me know if it's not big enough. Let's see if I can easily make it bigger. No, that's not big enough. 200%? Oh, does that work? Oh, yeah. I like. Is it good now? Yeah? All right. Been teaching for 20 years. It always looked big enough for me before, but now it doesn't. Getting old. Now, what that means in your brain is you take a regular parabola and you stretch it by factor 3, and then you move it up 5. There's the drawings. If you're good at this, you're like, okay, yeah, instead of going 1, 3, 5, like a normal parabola does, we go 3, 9, 15, and I move the whole thing up 5. If you're good at parabolas, if you're good at transformations, that's all you need in this part of the lesson. You're like, yeah, got it. Stretch it by factor 3, so it goes up faster, and move it up 5. Okay? Now, if you're like, yeah, I'm not so sure, I'm going to do it again but go through all the steps on how you get to this, okay? So take a second to copy that down, and then I'll switch over and do the basic version of that exact example. More time here? Yes, more time. Still more time? You okay? You good? I'm going to come back to this page in a second anyways. Let me go to I'm trying to graph y equals 3x squared plus 5. That's my goal. Over here. I'm going to put that over on my grid here. Y equals 3x squared plus 5. You don't need to copy all this down if you're pretty good at transformations. If you're not very good at it, you're like, I'm not even sure I could pull this off, then you're going to want to get out a piece of graph paper right now and go through these steps with me. Y equals 3x squared plus 5. Here's the steps. You need a graph of the base function. If on the test you're doing a table of values for every single base function there is, time is going to be a problem. You're supposed to know some of these base functions. But if you don't, if you get caught, you go, okay, I got to get some x values here. And then I just square all those. I'm just doing the base function here. Okay, so there's the table of values for the base function. I've just taken all those x values and I've squared them. This is actually a complete review of grade 10, grade 11, all at once. This is what a parabola looks like. Then what I've got to do is I've got to take those points and I've got to vertically stretch them by factor 3. That means stretch them all up by factor 3. And then I've got to move them up 5. And you can do that right on the table. You don't have to put them on the graph at all yet. You can say, hold on, let me do the vertical stretch right on here. So here, let me write it down at the top here. Vertical stretch times 3. And I just multiply each of those y values by 3. Now I've got a new table of values. And somebody last year said, can you just put a line through these old ones so I don't get confused? So I'm going to do that very, very lightly. I'm going to use my pen and like a blue pen and just say, well, I'm not using those anymore. These are my new points on my graph. Then, what was the last thing I had to do to this thing? Up 5. So I'm just going to write a little note to myself. I'm moving everything up 5. So I'm just adding 5 to all these points. And I'm going to draw my little line through those last set of points saying, well, I'm not using those. Those were just me thinking about what points to use. I'm going to take all those points and do that. And now I've got a new table of values that shows exactly what I want on my graph. I want negative 3 comma 32. Okay, I know I can't graph 32 on there, but it does tell me something. It tells me, okay, start from up here. You know, I'm way up here. Then negative 2, 17, still too big. Negative 1 comma 8, there it is right there. Then 0, 5. Then 1, 8. And then 2, 17, it's gone off the page. Like that. Certainly enough to answer the questions we were answering earlier. Max mins, domain, absolute mins, absolute maxes, increasing, decreasing. That's more than a good enough graph to do all that. But if you actually ask for the graph, this has specific points used right from the table. Any questions about that procedure? If you're a little better at it, you don't need the table to do those things. You'll just take the point 0, 0. You'll vertically stretch it by factor 3 and move it up 5. You'll take the point 1, 1. You'll vertically stretch it by factor 3 and move it up 5. You can do all that work right on the graph if you're comfortable doing that. And maybe the comfort comes from doing a few questions. And you get to the point where it's like, boom, done. Then you can also check your answer in Desmos when you're working on this to make sure you got it all right. Any questions about that one? More time? Who wants more time on that one? Does that kind of help with those to go, okay, that's the plan I got? It's not fast. I'm not going to pretend it's fast. You know, they go through this transformation homework like this is taking forever. Yeah, I know. It's not a quick procedure. Not at all. You will get faster at it, though. As you get to know the functions and get to know the transformations, everything will come a lot faster. More time here? You're good? Back to the regular presentation. Move down a little bit. Move this over a little bit. And here's the basic thought pattern that has to go on. You first decide what base function you are. You've only got those 8 choices from the previous page. And this one's a giveaway, right? It's the only one with a square root in it. The base function is square root of x. Then you look and go, okay, what transformations have been applied? There's a 1/5 multiplied inside the function. This one's weird. So even if you're like, yeah, I totally get all this. I did a zillion of these in grade 11. I don't know why you're redoing all this stuff. You might want to tune in for this. This is one of the little tricky transformations that's there. And I tried to put it on my table here. If there's a multiplier inside, it's a horizontal compression or it's a stretch. It depends on what that number is inside. And I want to go back to this translation here. See this? The number inside, if it's positive, you go left. If it's negative, you go right, which is completely counterintuitive, right? You'd think that positive numbers would make it go right and negative goes left. Here's a little catchphrase for transformations. The stuff inside the function, because it's inside the function, does the opposite of what we think it's going to do. That's a great way to remember it. When I go back to this thing, and there's a 1/5 there, that automatically tells me compression. 1/5, isn't that? When you do 1/5 of something, you're getting smaller. But the one in the brackets always does the opposite of what you think it's going to do. And so what you get here is a horizontal stretch of factor 5. Now do you see why in that chart I wrote it weird? To give you a heads up to watch out for. This 1/5 actually, instead of being compression by 1/5, it flips and say stretch by factor 5. Instead of the x values becoming 1/5 of what they do, they get multiplied by 5. If you want 1/5 to like divide by 5, but actually what happens is you multiply by 5. Very strange thing that happens inside functions. Now, if you're really good at transformations, all you need then is, okay, I know what root x looks like. There's root x there. Oh, sorry, there's root x there. Let me label those on there. It's not easy to see. There's y equals root x. Is that one there? And then horizontal stretch factor 5, it gets stretched out there. If you're really good at these, you're like, that's all I need. I get it. You got to stretch this thing by factor 5. But if you're like, I'm not really polished at these things, then I'm going to show you the other way. All the steps, yeah? Ready to switch over? Ready to switch over? Okay, so I'm going to come right back here. So if you're not ready to switch over, you just yell at me when I get back to here. Now, they want me to graph, over here, I'm going to graph y equals square root 1/5 x. If you need all the steps, which, again, I have no judgment for that right now, use all the steps if you're having trouble with these. Make a table of values for the base function, which is y equals root x. Now, here's where it helps to really know your base functions, at least the shapes, to know what root x sort of looks like. Because if you start subbing in negative numbers in this, and I'll do it here, but don't copy this down yet. This is me having a brain cramp maybe. I go, okay, yeah, Mr. Todd said make a table of values, sub in -3, -2, -1, 0, 1, 2, and then you go, all right, I need the square root of -3. Let me get my calculator out because that's a little weird to me. And I punch it in. Square root -3, and I press equals, and your calculator does something like this and goes, and basically what your calculator is telling you is that it's basically going, do you know what you're doing? What are you trying to do there? Are you crazy? Square root of -3, you can't take square root of negatives in the real number system. Okay, but later, right? You can't take square root of -3 and get a number that we can think of, that we're used to. You're not going to get any numbers like that. And so that's what it's telling you on the screen. It's like, you better check again, yeah? So if you want, I'll just put x's. No, x is a bad choice. I'll put no. I can't take the square root or any of those things. And that's where having the shape of the graph in your mind and knowing these base functions, where you don't have to go through all this. You know, I know what to start at for square root. Don't start with negatives. start with 0. And square root of 0 is 0. Square root of 1 is 1. Square root of 2 is like 1.4. And you might be like, oh, decimals, really? Am I really going to transform decimals around? And the answer is no. You really, like, that's painful. You could put those on there, but it's not the greatest choice for, and I'm going to just put my fake blue line through this, go, yeah, I'm not going to use that. What's the next one I should use? What can I take the square root of? Square root of 2 gives me a decimal. Square root of 3 gives me a decimal. 4. So I'm going to modify my table of values, because you get your choice on this table of values. You're just getting some points you can use. 4 would be a great choice to take square root of, because I get a nice point I can use on the graph. What's the next one? What's that? 9. I'm not saying you shouldn't use the ones in between. You can. You can use 5, 6, 7. There's no problem. You're just going to get decimals the whole time, and those are tough to graph. Yeah? So now I can graph these points. 0, 0, 1, 1, 4, 2, 9, 3, and now it's off my page like that. Now, incidentally, if you're right with me, if you're like right on top of all this math, this is just the 1, 3, 5 pattern that you learned in grade 10. 1, 3, 5. It follows that exact pattern. It's just sideways because it's a sideways parabola. Do you need to know all that right now? Well, no, but if you're thinking about those things, that means you're in great shape here. Next. What was my horizontal stretch factor 5. So that's to do with x values. Horizontal stretch times 5. So this these are gone, right? So I multiply the x values times 5. This is 0, this is 5, this is 20, and this is 45. My goodness. Jumps right off the page here. So my points now are, I'm not using these x values anymore. I've got a new set of x values that I have done the transformations on. So I get 0, 0. That's on the new graph, yes. Then I get 5, 1. And then I get 22. You see, you can't graph 22, but it does tell you where you're going to. 22. So you know that you're like, see how it's been horizontally stretched by factor 5. What questions do you have? The goal of this lesson, when I sat there at lunch thinking about it, the goal of this lesson is wherever you are with transformations, whatever number you would say your proficiency is, you're like, maybe I'm like a 20 on transformations. Hopefully by the end of the lesson you're like a 50. You're like, okay, I think I got a better chance of this. If you're an 80, hopefully you're going to be a 90 when we're done. You're like, okay, I can really do these. Do you have questions here? I'm searching for those frowns. Maybe your lunch is set in. I don't even have enough strength to frown. I had McDonald's for lunch. What did you have at McDonald's, by the way? Just the drink? Chicken nuggets. Chicken nuggets have come a long way, though. It used to be you went to McDonald's, like 15 years ago you went to McDonald's. The advice from everybody was, don't look inside the chicken nugget, basically. Now it looks pretty good. It's pretty white meat. But it used to be, you bite it and look inside and go, oh, no. You ate it in one bite because you didn't want to know what was inside, right? It's much better now. Questions there? More time? Back to the regular transformation presentation. Or flip chart. Look at this mess. And actually, 3 to the x isn't done enough. It's supposed to be done in grade 11, and you might be, okay, squared, square root. Yeah, I got those. You might want to really tune in for this one, because 3 to the x is a more difficult one because you haven't seen it as often. So, all sorts of transformations going on there. This time the x is up in the exponent, so what whoops. Just jumping around on me there. The base function here is y equals 3 to the x. And if you're like 3 to the x, I don't know that one at all. That's good. I'm gonna take the approach with the other version of this that I'm doing at the same time of dealing with this if I don't know what's going on. Now, if you do know what's going on, then you go through this list and you go back to your other chart and you go, okay, what does a negative out front do? What does a negative? Yeah, I see some people making the hand motion. So there's people that sort of have this down pat at some point. And all they know that you don't, if you don't is what's going on in this chart. Where to find these things. A negative out front means a vertical reflection. A 1/5 out front, it's outside the function, so it does what we would expect. 1/5 would compress it. A -5 inside does the opposite of what we think, so it goes right 5 instead of left 5. And then -2 out there is down 2. So I've listed those all. Keeps jumping on me. There, I've listed them all. There's the 4 transformations we have to get ready for. Now, if you're good at these things, that's more than enough information. That's like, okay, I know exactly what to do. Keep pressing the wrong button. Over here comes the graphs. There's the original graph of 3 to the x. If you're like, I don't even know how to graph 3 to the x. That's no problem. I'm going to do that in a separate example in just a second. And then when you take this thing and vertically reflect it, move it down 2, and do the stretches and moving over, you see it's moved over and down. And for people that are good at these things, that's all they need is go, oh, I see what you're doing here. You've taken this thing, you've reflected it. You've compressed it by factor 1/5. You moved it right 5 and down 2. Right? And you're like, yeah, I got it. But you're like, no, you're going to have to do way better than that. I don't really know how I would build that graph. I'm going to do that whole thing in just a second. On a separate sheet, I'm going to go, okay, let's go through what it takes to graph an exponential. And again, an exponential is not a common one. You don't see that as much. You don't see it in 9, 10. You only see it for a few days in grade 11. But for you biology people, exponential is it. Of all these functions, if you're thinking biology, chemistry, exponential is where it's at. That is the main function in those fields. Need more time here? Who needs more time here? Okay. Maybe all you came for in this lesson was, how do I graph y equals 3 to the x? Here it comes. X, y equals 3 to the exponent x. Because remember yesterday I said, oh, if you want to get to know some of these base functions, just build a table of values. And I went home last night and went, I don't know, they looked unsure about all that. So maybe I'll go and build the table of values for all of them. So you've got records here. You can go back to the video, or you can go back to your records of this and see how to build all these. And I'm going to approach 3 to the x like I don't know anything about 3 to the x. And I'm going to build some x values that as if you don't even know the shape of this thing, okay? So I'm going to choose x value, -4, -3, -2, -1, 0, 1, 2, 3, 4. And I'm going to plug all those into 3 to the x and see what kind of numbers I get. And these numbers might look mysterious to you. And this is one of those moments in the lesson where after I get these points, if you're confused by what's going on, you should definitely ask me. Now, I'm going to need some more space, so I'm going to pull this trick off here. Just buy myself a little bit of space here. There. Okay, so calculator. 3 to the exponent. 3 to the exponent of -4. 0.01. Mysterious. File that away. When I get to the thing, it says, do you have any questions here? Maybe your question is, how does 3 to the -4 become 0.01? And I'll do it. I'll talk about it. But for now, let's just trust the calculator and do 3 to the power of -3. 0.03. 3 to the power of -2. 0.11. 3 to the power of -1, 0.33. It's not a miracle I can do that, by the way. I just know one little thing you might not know is why I can get that answer. 3 to the power of 0, you plug in your calculator, you get 1. 3 to the power of 1, you get 3. 3 to the power of 2, you get 9. You can type those all in and get all those numbers. So if 3 to the x were to appear on the test, you'd be like, I forget 3 to the x. All right, just a second. Little table of values. And maybe you'll get reminded as you're graphing these things. -4, 0.01, that's like right on the axis. Well, it's not right on the axis. It's really close to on the axis, but it's not quite there. And then this is not much better. It's like right on the axis. -2, well, that's a little higher. -1, oh, that's coming up then. and then 0, 1. Now here we go. This is why this is called exponential growth. Watch what happens here. This is COVID cases in Ontario right now, right? Then, oh yeah, everything's fine. No, oh, that's up a little bit. Not too bad. We'll be okay. Yeah, no. Ooh, maybe we should start shutting some things down. Whoop, whoop. Yeah, this is what they're scared of. Yeah? Hospitals can handle this. Hospitals can't handle this. Watch. Just for fun. Yeah? Gone. Can you see the graph, the shape of the graph here? On this side, heading towards 0, but on this side, taking off to infinity and fast. The fastest we've seen so far of any function. Just goes off like that. If you're wondering about this, it just gets closer and closer and closer to 0, but never actually gets there. It gets so close to it, as close as you ever want to get to it, as many decimal places you want, but never gets there. There's 3 to the x. Now, that's not the graph they wanted. They wanted y equals, I completely forget now, exactly all the transformations we were supposed to do. Negative 1/5 minus 5 minus 2. That's not it. That's it. Negative 1/5, 3 to the x minus 5 minus 2. Did I write that the way they write it? Sometimes people get mad at me because I don't write it the exact same way. The 3, only the 3's in brackets. Okay, so you got all these things to do to this graph. Let's see, that's a y, that's a y, and that's a y. So I really do need more space here. Let's see if it's going to let me just grab, oops, no. Can I just grab that much? Oh, yeah. Eek, squeak. I'll just squeak that over there. Garbage can. Put down there. All right. Good. All these things I got to do, one at a time. Out front, back to your chart. The negative out front is a vertical reflection. Positive y's become negative, negative y's become positive. So if you want a shortcut, you just do, you just go, I'm going to use orange. Negative, 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 negative. Yeah? Vertical reflection just means take all those things and flip them over. Then, vertical compression factor 1/5. What the heck? Okay, so I got to multiply all these by 1/5? Well, yeah. Or you could divide them all by 5. Then you're going to need your calculator on exponential. Now, the thing about exponential, though, is how many of these points do you really, really care about? Yeah, just these 0 to 4 ones. Yeah, just when you take off from here. I know what's happening here. It's heading towards the asymptote there. And so to divide all these by 5, I'm just going to focus on these points, okay? Don't believe me? Let me just focus on these points, and then we'll see if we really need those ones, okay? So I'm dividing them all by 5. So I get negative 0.2, negative 0.6, negative 1.8, negative 5.4, negative 16.2. And these are too big to graph, right? So those are the only points I'm really going to focus on. I divided all those things by 5. Let me write that down. Vertical compression. Vertical compression 1/5. And the last two steps are write 5. And so this becomes 5, 6, 7, 8, 9. And then over here, down 2. Negative 2.2, negative 2.6, negative 3.8, negative 7.4, negative 18.2, because I've gone down 2 on all those points. And then I just graph those points, and I'll do it in blue. 5, comma, negative 2.2, right about there. 6 comma negative 2.6. So that's coming away from that a little bit. 7 comma negative 3.8, right about there. 8 comma negative 7.4, right about there. Okay, you're worried about these decimals maybe. You're like, well, Mr. Todd, what if I don't get this in the exact right spot? Well, no, I'm not going to look at it and go, oh, that looks like 7.3 to me. That doesn't look like 7.4. If you watch me mark these, you'd be like, oh, he's not worried about it at all. I'm looking for this shape here and enough points that I want, oh, you found some points, some good points here. Finally, 9, negative 18.2, that's off the charts. Now let's talk about this. What's it approaching? Where is that asymptote now? Finally, let's talk about the asymptote. The original graph has what's called an asymptote at 0. It's approaching 0. And stretching, compressing, moving left, right, none of that ever affects where that thing is. The only thing that affects where that vertical asymptote goes to is this negative 2. That asymptote's now been moved down to negative 2. And I sort of see that in my table, that the numbers are getting close to negative 2. And you see why I didn't need all those points? I go, oh, I know what's happening here. It's approaching negative 2. And I sort of banged into it there now because I was drawing it really quickly. But that's where that is. And where do you find it? That right there tells you where to find that asymptote. Any questions about that giant mess? I think that's about as hard as it gets in grade 11, to be able to do all of those things at once with a function that maybe you haven't used all that much. When it's with x squared, you've got some experience with x squared. You got some experience with the lines. Even square root doesn't seem that weird, but 3 to the x is a weird one. Tell me, questions? Why does 3 to the negative 4 come out to be 0.01? That might be the question I would ask if I were you. How is that even happening? Yeah, like negative exponent means you're dividing by something. And not only just dividing by something, you're dividing by 3 4 times. So divide by 3, divide by 3, divide by 3, and that's why you get these really small numbers. Negative exponents seem mysterious, but all they mean is, no, we're actually dividing here. We're not multiplying. When you first learned about exponents meant multiply by something a bunch of times. But negative exponent means divide by it a bunch of times. More time here? Just a look ahead. There's 2 types of homework for this section. There's the regular stuff, and then it says supplementary problems. Here, you got to get good at these. You've got to get good at these. So if after doing the regular homework you're still struggling with every single one, that's what the supplementary is there for. Is that you can go through and go, yeah, let me just find a couple more. I'm not saying do all the supplementary. It's there. It's like, I still struggle with exponential ones. Okay, I'll go after a few extra exponential ones. Okay, so when I write it up there, you'll see there's 2 kinds of homework. Only worry about the first part, unless you're having trouble. If the first part goes well, then you're done. I'm not done, though, with the lesson. We're done here. On to the next. I want to go back to best fit. There we go. Let's discuss some other functions, though, and then here's your job. Most important job left today is that if I do a function up here that you're like, by the time I write down a couple things, if you're not confident you could graph it, you got to let me know, and I'll go over to the other board and do the whole thing again. All right? Some functions for discussion. I don't think you have a lot of places to write here, do you? I'll try and write the way you're going to have to write to fit in there. Here's the base function. Base function, y equals x. Transformations. Here, let's quiz you right here. Let's act like this is the quiz. There's no quizzes in this class. Let's just act like this is the quiz. Test yourself right now to see if you know what's going on. First question. How many transformations have been applied here? Can you see? Yeah, there's 2 of them. We got to deal with the 3, and we got to deal with the 7. What does a multiplier of 3 out front of a function do? Okay, good. It's starting to happen now. Vertical stretch. I just write times 3 because that tells me a lot about what I got to do. I got to multiply things by 3. Then, what does an add or subtract outside of the function do? The function's just x here, so it's pretty easy. Yeah. And your grade 11 teacher might have been right on about this, and you had to write all the words. Vertical translation up 7. I'm past all that. Up 7 will do. Yeah? We're trying to get to answers here, and we got other things to worry about. Up 7. Sounds good. Yeah? Do you feel confident you could then graph this thing now? If you're out there going, wait. Didn't we? Isn't this just y equals mx plus b? Y-intercept 7, slope 3? Absolutely. And that's really what this is saying right here. Move it up 7, so don't start at y-intercept 7, and then vertical stretch by 3. Instead of going up by 1s, you're going to go up by 3s. So it really is the same thing. But if you want to graph lines using y equals mx plus b, you go right ahead. When we go to calculus, we'll switch right back and we do a lot with lines again, and we'll just use y equals mx plus b. But let me know. Anyone feeling unconfident about this one? You think you could take a shot at this one if you needed to? Okay, I'm just going to keep going like this. There's, how many more is there to do? 6. As soon as I get to one you're like not feeling confident about, you tell me, I'll switch right over to the graph and go, let's do this one. Let's totally do it. Base function. Again, I'm going to try and quiz you here. What base function are we talking about if it's 1 over x minus 7 plus 5? Y equals 1 over x. And then I got transformations. I hope I'm writing this up in a way that you can sort of fit it in the space that's on your note there. Quiz yourself. How many transformations do you see here? 2. Yeah, there's 2 there. There's this subtract 7 inside the function, which means write 7. I'm not hung up in the horizontal translation by 7 units. Those also sentences. I don't care about that anymore. And then over here, up 5. I believe I did a 1 over x today in the previous lesson. In the key properties lesson, I graphed a 1 over x for you. But is it someone that would like to see me do this whole thing? Would you like to see this whole thing? Would you like to see the whole thing? Yeah, okay, let's do it. 1 over x minus 7 plus 5. One over x is a strange one. It really helps to know 1 over x. It really helps to know 1 over x where you don't have to go through a whole table of values. It helps to, at least in your brain, by Thursday or Friday when we have the test, to be able to know what 1 over x kind of looks like. Because the table of values, to be honest, for 1 over x can be not that helpful. You can do it. What you'll get is something like this. And for some people, that's not very helpful. 1 over x is the one where the table of values doesn't bear. You have to have just a little bit of knowledge of 1 over x. But let me graph those points and see if it at least gives us a hint as to what's happening. 1, 1. 2, 0.5. 3, 0.33. Negative 1, negative 1. Negative 2, negative 0.5. Negative 3, negative 0.33. That's what your calculator will spit out. You see how that can be less than helpful, unless you already knew what was coming. You're like, oh, yeah, now I remember. It's that guy there with the asymptotes and everything like that. The error does help, actually. And we're going to do a lot of this in Chapter 5. The error tells you, no good. And I'm drawing a dashed line out there, and that's mathematically exactly what we do. We draw a dashed line letting everyone know there's a vertical asymptote here. Do not go through there. Not allowed. Yeah? It's like Gandalf's staff sticking down there going, thou shalt not pass. That was really funny 10 years ago, I got to tell you. Sort of aged, that joke. But anyhow, hopefully that's enough to get the rest. If it's not, you're going to have to use some weird x values. Some weird x values that would really help here would be negative 0.5, because you'd get negative 2, and 0.5, because you'd get 2. And that really maybe does what you need to help get this picture of that graph there, yes? I got to be honest, though, you'll find it much easier with 1 over x if you can just walk up, draw the asymptotes, draw the ones on, and go like that. You'll find this way easier to draw if you can just plunk that all on there like that. 1 over x is one of those ones where it's like, you don't want to be leaning on the table of values. Some of the other ones, table of values bail you out. This one you better get to know, Because actually, this is really straightforward. And I'm going to take a second and erase all this and show the way you really want to be able to draw these things. I need a giant eraser. I'm going to get rid of all that, only in the interests of clarity. And I'm going to go right after this thing. Right 7, up 5. So, the vertical asymptote has been moved right 7. It's not at 7 anymore, it's been moved right 7. The horizontal asymptote has been moved up 5. And if you know 1 over x well enough, you know, okay, there's a point sort of at 1, 1, and negative 1, negative 1. And can you totally see where 1 over x is going to be now? So good, Move the asymptote, and there's the graph right there. Okay? So my strategies I've been giving you, which is table of values, transformation on the table and everything like that, that all works for this one, but this works a whole lot better, that you know 1 over x well enough that you can just go bang and nail it down. Yeah, for sure it is, because there's no really good reference points here. What I'll be looking for is the 2 asymptotes, those initial points, and there really only is 2 really good points on this thing. It doesn't ever do any other whole numbers there, and then approaching the asymptotes either way there. Good on that one? Good, I'm glad you asked about that one. I'm glad we got a chance to talk more about that one. I'm trying to over-explain everything here in the middle of COVID, advanced functions in quadmesters and everything like that. But I'm not going to over-explain this too much. This is parabolas, yeah? Parabolas should be pretty good by now. But there is a problem with this one that we got to talk about, and I got to warn you about, because it will come out in the test. I have to. It's such an important little thing, little thing that comes up in this course, in later courses. We just have to be able to, it's like a spider sense you got to develop. When you see something like this, you're like, whoa. Hold on. Let me just work on this a little bit before I do anything. What's the work on this step of this thing? Little math praying there. The exponent is an important thing because that tells us about the base function. This is an x squared. It's buried down deep inside, but this is an x squared. Big problem. Yeah? All these transformations are set up to work with x by itself. And it actually is in my table, sort of. You see that x is by itself like that? Yeah? So if that's a problem, one great tactic on tests is as soon as I hand you the test, is people write stuff at the top of the test immediately, like, don't forget this. Yeah? And I would think I would just write common factor at the top of this test. You can write that on every test from here to the end of calculus, actually. Common factor comes up so often, and it's such a mess when you miss it. That's such a simple thing to do. So watch out for that common factor. Let me rewrite this thing. As it should be. Y equals negative 4. I've done something else here to try and help you manage brackets. I never go circular brackets. I go circle, then square, then I go with the squirrely ones, and then back to circles. It helps me keep track of all the brackets. Those of you who are maybe going into computer coding know that brackets are a big problem, keeping track of all the brackets. Nice thing when you're writing it is you can do something like this. So I've added a bracket here. I've common factored out the 2, and now this thing's ready to go. Base function, y equals x squared. Transformations, vertical, reflection. Vertical stretch by 4. Horizontal compression 1/2. Left 4, down 15. And I did that fast on purpose because I want to challenge you a little bit to go, can I pick these out? But I don't want to challenge you too much. I want you to ask me. If you're like, whoa, where did you get that from? Then I want you to tell me now so we can see where we're at with these. Sort of good or sort of not good? Ah, good. That's the tough one. Even if you're really good at these, that's the tough one. The 2 inside, multiplying by 2 to me would be stretch. It just screams stretch, except it's inside, so it's not multiply by 2, it's divide by 2, which is multiplying by half. What do you do here? Flip this. It's got to reverse its roles. This multiply by 2 becomes a divide by 2. The divide by 1 becomes multiply by 1. So just flip over this thing. If it was a 2, think of it as 2 over 1 and flip it. So whatever's there as the fraction, flip it. You say, why don't you just say divide by 2? I could say that. It's not a bad thing to say. But then if this is like a 3/4 in there, nobody knows what to do. Yeah? So I just say, to handle all situations, flip whatever's inside there. The same way we did here. Plus 4 screams, go right 4. It's like plus 4. Except inside the brackets, it does the opposite of what you think it's going to do. It has to do with the location of these numbers. These numbers over here are on the opposite side of the equation of y, so they do what we expect with y. These numbers here are on the same side as x, so they do the opposite of what we think they would do. Great question. More. Tell me questions about this. This screams multiply by 2, except it's inside the brackets. So what's inside the function, we do the opposite. And so the opposite of multiplying by 2 would be dividing by 2, which is multiplying by a half. And I'm suggesting the move, whatever number you say there, flip it. And that'll tell you the right thing to multiply by when it's inside the bracket. So that's a weird one. If you're like, yeah, I sort of get all this. I don't mind this transformation stuff. Then this is one thing to watch out for, is this whole situation here and getting that down pat. Yeah, if there was like a 3/4 in there. Right, you could do that. Or you could just say, no, I'm going to multiply by 4/3. You just flip what's there into the reciprocal there. I tried hard to set you up for success on this first test by saying, here, I'm going to do this. This is what I'm going to put on the test. This is what you got to know. I'm not really doing that here. I got to warn you about this stuff. It's in the homework and everything like that. But and could something like that appear on the test? Yes, but that's not. I wouldn't lose sleep over that necessarily. Work on it, but more importantly, you can do the basic transformations that you see across here. Yeah. Other questions? I hope you're confident building a y equals x squared table and doing these transformations to that. No, because that one's x squared is not too bad. It's a pretty well behaved one. I think a second ago I said, hey, that's the hardest one. It's not. This is by far the hardest one. And this goes a step past what you'll have to deal with in any test in this course. I do want you to see it because it's difficult. You know, whenever I say that, I can feel people getting upset. They're like, if it's not going to be on the test, why do I care? Actually, the goal of the homework and of me and of the review is to ask you tougher questions than will be on the test on purpose. That way, when you get to the test, you know exactly how to handle the same thing. If I can explain why this is a common factor and show you how to common factor this, when you run into this, you'll be like, oh, no problem. I can do that. I can common factor that. You see? So it is a plan by math teachers to go farther in the homework than you need on the test. That way, when you run into a question on the test, you can handle it. This x is not by itself. It's got a negative 1/2 in front of it. So I've got to common factor out a negative 1/2. And I'm using square brackets there immediately. That's a calculus habit. I just finished a quad of calculus, and we always, because of what we're managing in calculus, whenever we common factor, we immediately use square brackets. And it'll be hard to explain why that's such a convenient thing, but I'll start using it here because it's a nice habit to get into. Common factoring out negative 1/2 out of x is really straightforward. If I take negative 1/2 out of negative 1/2 x, I've got x. Common factoring negative 1/2 out of 3, Hope that's not too subtle for them. If I take negative 1/2 out of 3, that's really hard. That's really hard. One way to handle it is to go the other way. I got to put something here. I got to write something in these brackets. And apparently when I multiply negative 1/2 times that, I'll get 3. That gives you a chance. What do I multiply 1/2 by to get 3? Half of something is 3. What's the something? What's that? 1.5. Half of 1.5 is not 3. He went the opposite way. 6. It's not the only way to handle this, but it is one way to handle it. When you got fractions in there, you're like, oh no, fractions, and your head just goes, oh, here we go. I'll show you another way to handle it in just a second. But take a look at this. Oh, is it going to be positive or negative? I got to go negative 1/2 times this thing and end up with positive 3. That's got to be a negative in there. That is really, really hard to think that. To, one, know that you got a common factor, and two, deal with all those fractions. You could do this, though. You could go, okay, I got the 3, and I'm taking out a factor of 1/2. Then you could go 3 divided by 1/2. And that can get you the 6. Yeah, so you can just handle it that way. But I promise, not a big setup to burn you on this test. I'm doing it now because it's going to come up in Trig. We're going to have to deal with it in Chapter 6. So I'll just nudge at it for now and just bring it up with what's going on there. So now, base function, 5 to the x. Transformations, horizontal reflection, horizontal stretch times 2, and right 6. I did those fast on purpose. I'm trying to challenge you a little bit, but I do want to know what your questions are. After I finish that, I want you to go, okay, where did you get this from? Where did you get that from? Let's try in your words, shall we? Where did I get the horizontal reflection from? Where's that appearing in all this? The negative inside there. That was in that chart I gave you at the start there. It says, hey, if there's a negative inside there, that's a horizontal reflection. How about the, okay, I'll do the right 6 first. That's easier, right? Right 6, negative 6, weird. Why wouldn't negative 6 be left? Well, when it's inside the function, it does the opposite of what you expect it to do. How about horizontal stretch factor 2? Can anyone explain that? Not using my words, but using your words to try to help out the people around you. Staring at this McDonald's drink. We're going to McDonald's for dinner now. Yeah. The ones inside, you can still do multiply. Just flip what's there. That's how you get the reverse, yeah? Flip by 2 over 1 and just flip that thing for horizontal stretch, okay? It looks like the 5 is part of the transformations, but the 5 is the base function. Now back to here. Finally, this comes up, this mystery that happened at the start of the lesson, right here. It said, oh, base functions, y equals b to the x. On your review of base functions, I used 2 to the x and acted like, oh, 2 to the x. But really what we mean by 2 to the x is you can have 2 to the x, you can have 3 to the x, you can have 4 to the x, 5 to the x. You can have 1.01 to the x. That's closer to what you'll use in biology, a base of increasing by a certain percentage. We don't know what that base is going to be, and they're doing all those calculations to COVID right now. What is the base? How fast is this thing going to grow? This base happens to be 5. I know it looks like a transformation, but that's the base. And when you go to build your table of values for your base function, instead of using 3 as the base, as I did earlier, you'll use 5 as the base, and when you plug in numbers, you'll get 0, 1, 1, 5, 2, 25. This thing will grow at a different rate because it had a different base, but it's not a transformation with the way we've presented it here. Yeah. Great questions. Other questions? I'm really trying to take questions and hit them out of the park. and just act like every question is awesome. Because it is. Every question, you must have heard this in math before. There's only one bad question. It's the one you don't ask. Doesn't do you any good to be sitting there at 4 o'clock tonight going, I wonder why he didn't use the 5 there. Doesn't do you any good. You need me here right now. That's why in class is so much better than virtual, right? You can look me in the eye and go, whoa, 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 what'd you do there? But you have to use me, yeah? Don't worry about what other people think about what you know and don't know. They don't know a bunch of stuff either. If you guys knew everything, you wouldn't be sitting out there, would you? You'd be having a nap at home, right? So ask great questions. More questions here? The negative inside the function. So right here on my chart here, horizontal reflection, when we've got a negative multiplier inside, that means horizontal reflection. The x's have become, positive x's become negative x's become positive. Good. Oh, yeah, he says, what if there is a vertical reflection with an exponential? And I think we did have one earlier. Am I crazy? My memory's telling me, yeah, right here. It'll be just out front of the whole thing. So that's what a vertical stretch would look like. Horizontal would be inside the exponent. Yeah, right. The exponent is like that. That's the inside of the function for exponential. The inside is what's. That's right. Vertical would go out in front of the whole thing here. Vertical shift would go outside over here. And again, I think, yeah, out there. These notes have been carefully designed that not every version of this is in the notes somewhere, but a lot of the versions are there. So when you're going to your homework, like, how do I handle that? Flip through all these and see if it was handled somewhere in the notes. We tried to get most of them in there. You know, every example is slightly different to try and cover all the different cases. And Desmos is there to bail you out. Just imagine, here, check out Desmos and all this. If you were approaching this one, you're like, I'm not sure how to do all this. Watch what Desmos can do. Desmos can go, okay, I want to know what does 5 to the x look like. You go 5 to the exponent x. Boom, you get that. You go, okay, what happens when I put a 2 out front? Sometimes it's even better to put it on a new graph. You go, okay, what about y equals 2 times 5 to the exponent x? And it color codes it too. You see there's one red, one blue. And then maybe, okay, what happens if I put a plus 3? Let me turn off that one. 5 to the x. And what happens if I put a plus 3 out here? Can you see it's moved up 3? Like, oh, well, what happens if it's plus 3 here? Oh, I didn't put it on this one. Plus, hey, stop that. Oh, it doesn't want to do that. Okay, yeah, you want to play, huh? How about some brackets? Not my first day, Desmos. You see how it's moved left 3? Yeah? You're like, Desmos can teach this whole lesson. I don't need you, Mr. Todd. I can just type them in here, and I can see left, right, up, down, vertical stretch, you know, do that whole thing. And that's true. When stuck, don't forget about Desmos and all this. That was fun. Desmos mocking me. Hey, you got $5 to bet on a function being there on the first page of your test that you have to be able to graph? This one, y equals absolute value. Let's go through all the steps. Let's not play around with this. Let's make sure you're ready for this. What do they want? They want y equals, I've forgotten already, -4, absolute value of x minus 7. You totally forget. Brain explodes. Come test time, you're like, absolute value, I can't believe you asked absolute value on the graphing part of it. Of course I did. You go over here, you go, okay, just a second here. What I do remember what absolute value is, when you take the absolute value of a negative number, you just get the positive version. That's all I remember about absolute value. And it's enough, actually, here, to be able to handle the situation. I have a beautiful table of values for absolute value. Hopefully you're a step along where maybe you don't even need the table of values. You're like, I know what this is going to look like. I get the big V for victory there. Then, negative out front. Slowing down here to give you a chance to processing. You can see the little the processing thing on the computer when it's thinking. See that all on your foreheads? You're like, do, go through the information. What does the negative out front of this thing do to everything? Vertical reflection. Let's take the y values. If they're positive, they become negative. If they're negative, they become positive. Let me write that up here in another color. Vertical reflection, -3, -2, -1, 0, -1, -2, -3. If you're right with me, you're like, oh yeah, all that did was take this thing, and the v was like this, and now it's going to be like that. How about a 4 out front? Multiplier of 4 out front. Quiz yourself. Vertical stretch times 4, so -12, -8, -4, 0, -4, -8, -12. So now here's the absolute value dance. I was here, and I did this move. If there's ever a school dance again, you can do the absolute value dance now. Yeah. Start here. Vertical reflection. Yeah, you can have a call out. Everyone vertically reflect now. And you're like, oh, everyone vertically stretch factor 4. Okay, yeah. How about this -7 inside the brackets? Processing. Which way? Translate. Good. Do you see what he did? He did the cleverest thing I've seen so far. I saw him flip, and I think he flipped to this thing. Yeah? Use it in your homework. Just have this thing sitting there every time you do a homework question until it's like, I don't got to look anymore. I know what they are. Which way is it? Right 7. I've lost it. There it is. Right 7. So right 7 means take the x values and add 7 onto them. Right 7, so I get 4, 5, 6, 7, 8, 9, 10. And then, let me get the highlighter out. Another way of approaching this is just say, after you do all those things to your table, you're graphing those points there. 4, -12. Okay, it goes off my grid here. If you're using regular graph paper like I suggest, you don't care about going off the grid because you'll just extend your grid down. You know, that's no problem. But it is helpful when you know it's 4, -12. I know it's down here somewhere. Next one, 5, -8. 6, -4. 7, 0. 8, -4. 9, -8. And hopefully you have at least a little knowledge of absolute value. You're like, oh yeah, wasn't this the v thing? So you know it's straight lines here. And technically, we should be labeling these every time and labeling what the graph is. You have questions? More time? Okay. What time do I got to wrap this up by? 2 o'clock. And then teach again right after. Oh, aren't we good? And we're still a lesson behind if I do that. I got a plan. I have 2 plans, actually. I'm ready. I think what I've done here today is very important, though. I'm not bragging. I'm just saying, you know, we got to get to the bottom of these transformations. There's no sense going on to other stuff if we can't be awesome transformers. We have to be, you know. Another joke that's 8 years old now. No, wait. When did Bumblebee come out? That's only 3 years ago, right? You guys are still into Transformers, aren't you? Some people are like, don't want to admit it. I watch Transformers when no one else is around. More time here? I don't remember where I am. Here, just back to here. I did that one, yes? Oh. Just a little warm up on trig, okay? I'm going to do this one quick. If it blows right on by you, that's okay. No trig on this test. This is just where you're supposed to be on trig by this point. And so if you're not there with trig, you can be well prepared that on day 1 of trig, you're like, I got to start listening because the trig isn't my thing here. Here's what you're supposed to get out of grade 11. You're supposed to get out of grade 11 that we always have to common factor That's what I was warning you about. We have to be prepared for common factoring when we get to trig. And I've common factored that 3 out of the inside. And then in trig, we had different names for all these transformations. We talked about exponential being the function of biology. Sine cosine is the function of chemistry and physics, anything to do with waves. Any wave behavior, sine and cosine is involved. So we have new names for these things. Vertical stretch is not called vertical stretch. It's called the amplitude. Do you remember this word from grade 11? Some nods, some skeptical looks. It's just a new word, so don't freak out. This is the vertical stretch. We call it the amplitude. Why? Amplifiers. I don't want to get carried away with this. I'll get really excited about it. When I press the volume on this, I'm changing the amplitude of the wave that's coming out of the speakers. I'm just amplifying. I'm making the waves bigger. That's why. Vertical stretch. Amplitude. Yeah. What else? Period. 360 divided by 3 equals 120 degrees. Because normally the period of cosine is 360 degrees. This has been compressed by factor 3. Now it's got a period of 120. Does that ring a bell a little bit? No. Well, don't freak out. You use this as your guide to maybe doing this homework a little bit. And I'm going to add some words to this in just a second, okay? For surviving this in the homework, knowing that I'm not asking any trig on the test. I'm just trying to warm up for chapter 6. And then the last parts is phase shift. This will look familiar. Right 60. And vertical translation, that word hasn't changed. Down 4. So this here is the vertical stretch, but it has a new word. And this here is horizontal compression 1/3. You can definitely do those questions that way. When we get to trig, we'll do it this way. And if you're freaked out by trig at all, just totally skip those questions. And have faith that Mr. Todd, when he comes sailing into Unit 6, will do the same thing I've done in this chapter, which is I'll take the time to go over what we need to get the basics down pat. So if trig is freaking you out, relax, go on Amazon tonight, order a shirt, I dig trig, get a positive attitude about it, and we'll address it right around Christmas time. It'll be my Christmas gift to you. Some trigonometry, yes? You think that's funny. You go type in I dig trig, and there'll be shirts that say I dig trig. Yeah, it exists. I'm not making that up. So good enough for now, okay? I just wanted to nudge at that a little bit to get the rust off your brain a little bit from that, or to get you scared enough to pay attention when we get to trig, yeah? Okay, I tried to handle this with my little chart, so this isn't a big deal. Sometimes we don't know what the function is, actually. We won't know the equation of the function, but we can still talk about its transformations. And that's what I was referring to here. I can talk about vertical stretches, compressions, translation, all that stuff, without actually knowing what function I'm talking about yet. And that's what this last part of the lesson talks about, is it says sometimes we may need to work with functions whose equations are either unknown to us or very complex. When working with these functions and the graphs, however, we can easily use general function notation to describe transformations. They talk about COVID and flattening the curve. We don't know the exact equation all the time, and the equation changes as we go. We still can talk about vertically compressing the curve so it flattens out a little bit. We can still talk about those things without knowing the actual equation. What does this mean? Well, think of a graph of any function you want. Any function you want, and we'll think of the COVID curve. It wants to do this. That's what it really wants to do. And we just represent that function by f of x. We're going to talk about it. Okay, f of x is the COVID curve. Now, could we represent it after it's been vertically stretched by factor 3? We could say, okay, if we all stop wearing masks, we're going to stretch this function, and it's going to start taking off a lot faster. We move up 5. What would that mean? It means we test more, and we find out there actually is more cases out there than we thought there was. We still don't know the equation, but we can still move it around and talk about what's going to happen if we stop wearing our masks or do whatever. Sounds like I'm throwing in a COVID lecture in the middle of this. No, I'm just trying to attach it to something that's been in the news. So for instance, if there's a 5 in there, we can still talk about it's horizontally compressed by factor 5, even though we don't know what the function is. If there's a negative out front, we can say, oh, that's a vertical reflection, and we still don't even know what the function is. We can go right 2, up 3, we can do all those things. We can common factor, all of that stuff, do all those steps, and we never know what the function means, and it's still valuable information. And COVID's the perfect example. We don't know the exact equation, but we can still talk about what different things we could do are going to affect that curve. I'll give you time to copy those down. "20 minutes. This example you don't have to copy down. This next example, this graph example, because they do it for you on the next page. Yeah, I've given you the full here, but on the test, just enough that I know what you're talking about. I'm not hung up in the language. I think grade 11 teachers very much focus on that language, and it's important to have in the back of your brain. But for me, I just want the results. I want to get, you know that's up 3 or left 4 or whatever. This curve that's given here could actually represent some of the things that have happened in COVID along the way. We're really hoping, hey, COVID cases are going up, and we really hope they're going to come back down again and not come up again. And then we could talk about what happens if you move that thing up 3. Well, you just take the whole curve and you move it up 3. I don't know the equation of this curve, but I can still talk about moving it up 3. Or I can move it up 5 or down 2. And that's what the pictures show on the next page, is they show you, oh, I can take this graph and move it up 3, down 2, whatever you want to do without ever knowing its equation. And you don't have to copy anything there because the graphs are all there. Do you need more time here? No? Okay, so that's what they show here is they show, okay, I can take this base curve and I can move it up 3, I can move it up 5, I can move it down 2. I don't need to know the actual equation to be able to do those things to it. And that's more of what it says here. Consider the function g at x equals f at x plus 2, which seems very strange, but all they're trying to say is g at x is this function moved up 2. That's all. Yeah? So nothing too crazy there. You can read through the paragraph, but I hope the way I've taught this, that doesn't seem too weird at all. And we don't need this right now. That's setting up for a calculus example, and I will deal with that later in the course, but we don't need that right now.